Ahead and get started. So welcome everyone to this webinar as part of the Statistics and Data Science and Aging Interest Group. Before we go ahead and get started, we just have a couple housekeeping items. First and foremost, our interest group would not be possible without the ASA, and our activities would not be possible without the help of some of our sponsors. So I want to acknowledge our founding sponsor, which is the University of Maryland School of Medicine, as well as our additional individual donors. If you'd like to participate, you're more than welcome to. Also, I realized that some people, find their way into these webinars who are not necessarily members of the Statistics and Data Science and Aging Interest Group. So we're happy that you found us. Once I'm done talking, I will put a link in the chat so you can find out how to join us, and you can join us for free. Now, with that, I am going to introduce our speaker. I am very pleased to introduce you to John Boscardin, who is professor in the departments of medicine and epidemiology and biostatistics at the University of California, San Francisco. He's director of the Statistical Laboratory for Aging Research. He co-leads the UCSF P30 Pepper Center Data Analysis Core, and he's also co-leader of the Analytics Core for the joint ADRD-PO1 program project between UCSF and Mount Sinai. His lab is comprised of 10 full-time data and statistical scientists and provides deep analytic support across the full life cycle of research projects. He's also a longtime core faculty member for the CTSI Case Scholars Program. He serves as statistical mentor to numerous early-stage investigators. Dr. Boscardin received his PhD in statistics from UC Berkeley and was a faculty member at UCLA in the departments of biostatistics and medicine before joining UCSF in 2008. His areas of methodological expertise include analysis of longitudinal repeated measures and time to event data, treatment of missing data, Bayesian statistical modeling, and computational methods. So with that, I am going to turn things on over to John. So welcome.
Great. Thanks, Michelle. Appreciate you inviting me to give this webinar. And so, yeah, I know the audience consists of a bunch of people like myself who may be, directing statistical cores. And so I'll talk a little bit about our group and how we work and some of the things we do in general. And then I'm going to discuss some of the issues in kind of one of our main threads of work, which is building prognostic models, and some of the issues that arise in that. It's going to be a very applied talk. I'm going to review some of the work we've done, but probably mostly work that other people have done and that we've used in our pursuits. All right, let's see here. Okay, so yeah, I'm going to introduce our group. I'm going to talk about the use cases, talk a little bit about machine learning versus traditional regression approaches, and why we're mostly here today talking about the traditional regression, some of the issues in developing a model with a regression approach, how we do internal validation. I'm going to talk about this concept of the leaderboard of statistical models, and an idea we've been sort of thinking about a lot lately, which is the stability of individual predictions in these models we create. Okay, so I mean, this is a huge team science effort. I'm going to talk a little bit about the lab. We have 10 statisticians extraordinaire that are part of that. Most of my core collaborators are in the Division of Geriatrics at UCSF, but we have friends all over the university and abroad and further abroad, especially at Mount Sinai. We now have this joint PO1 with them. So, here's our lab, sort of prototype web page, which will hopefully be live one of these days. You can see we're a pretty big group. And, so I did want to talk a little bit about this lab. It's a little bit different than maybe how things work where you are. And, how do we do this at UCSF? So, UCSF, there's not a ton of sort of grad students and postdocs that do these kind of things. We are more focused on career full-time people. And so since I've joined UCSF, we've grown from 2 up to 10 core statisticians in our lab. As I mentioned, it's a real team science framework. We work, kind of deep longitudinal collaboration. I'm also interested in one of my hats in, short-term consulting, but this, the lab's efforts are mostly on kind of ongoing, long-term embedded projects. So the statistical scientist is kind of the key idea to me. They're part of the research group and they accumulate data, experience in the data methods and the substantive area. The researchers that we work with are interested in the methodological details of what we're doing. And often the projects will have more than one statistician. And so then we get this great mentoring occurring in all directions phenomenon, which seems to lead to, has been a pretty successful model. We work with people sort of in kind of a concentric circles model, people who are most closely related to the Pepper Center that we have. And but then we have to expand outside of that. I think in the current times, it's worth sort of briefly discussing our business model. How does it work to have a large statistical core of full-time people on soft money? So we have, two large statistical cores, one through the Pepper Center, which provides direct funding for a statistical core, but we also award pilot and training grants through the Pepper Center, which are often then sent back to the statistical core for support. We 5 years ago got a large program project grant with Mount Sinai that also has a statistical core. And so the two of those, together with a number of other individual investigator awards, sort of allow us to keep going. We try to spread our tendrils as widely as possible, especially in these days of funding uncertainties. Okay, so I'm going to talk a little bit about predictive modeling today, or prognostic modeling. And I'm sure many of you on this call are much more expert at this than I am. Some of you, though, may have been maybe thinking about this for the first time, and I hope to kind of everybody get something out of this at least. So why are we doing this? So there's a number of reasons that we develop prediction models for sort of things that happen to people. And, probably precision medicine and shared decision making are kind of the top two settings I'm thinking of here today, where we're trying to find predictions about what will happen to people and attach a probability to them. And that probability, 37% or 12% will mean something to the consumers of these prediction models, and they will be able to make decisions and act upon those probabilities. Certainly prediction models are used in a lot of other settings like case mix adjustment and propensity scores. Probably not going to talk so much about that today. Okay, so if you've never seen these, so they sort of have, many of them are very simple in their kind of presentation. So this is one like of the original kind of point scoring with the Framingham data set. So you find what age you are, you get some points for how old you are, you get some points if you're male, you get some points depending on your blood pressure, you get some points if you're a smoker, you add up your points and you can get your estimate of risk from a table, right? So continuous version of that that's still available in a table are these nomograms. You find out, what disease class are you and age and your GCS and so on. And then you get a points for each of those. You add up your points and then you can look up various outcome probabilities in the nomogram. Obviously most of this has moved on to the web or phone apps. This is one I really like, the NISQIP calculator. You input, maybe 20 things about the patient. And then it tells you predictions for a bunch of different outcomes and sort of displays them in a really nice way. Even if some of these are not particularly predictive models, just sort of knowing this panel of things that might happen to a patient when they undergo some procedure and have certain risk factors is of great use to a surgeon and deciding if this is an appropriate procedure for their patient or for the patient and deciding if this is something they might want to do. Some of my colleagues at UCSF, Alex Smith and Sei Lee, Eric Widera, have developed a website called ePrognosis, which has attempted to sort of curate a huge number of prognostic models relevant to older adults. It's kind of a nice front end to get in. You can sort of go on their webpage and then, you can obviously won't be able to see here, but this is sort of one of them. And you enter a bunch of stuff about the patient. And this is one to predict what might happen to older adults in community dwelling. And then after you enter all your things, you get like a nice little report here about, 5, 10, 15-year risk for your patient, average for a patient their age, for mortality, for disabilities of various types, and then sort of some explanation of how the tool worked. This is another example from our a paper we published in JAMA Internal Medicine, which I like the presentation of this because it sort of shows the heat map of the impact of each of the risk factors for sort of 10 hypothetical patients, and kind of shows their in this case we're actually predicting time, median survival time, and then 25th and 75th percentiles of that. Okay, so before I move on, I mean, I'll say that the point of this is to show there's still use, there's still interest in these types of models, these simple models that have a small number of factors where the consumer, whether that's a patient or a provider or caretaker, can look at how the model's working. They can get a little bit of a sense of what's under the hood, and that's important for them to trust the model and make use of it. It can't be, involve 100 things because it's sort of impractical for that use case. There's certainly, we'll talk in a little bit about, obviously that's not where things are going in the world, and and yet there remains this sort of need for these types of simple prognostic models. Okay, so, what about our kind of typical settings that we see in our group? So we do a lot of work with the Health and Retirement Survey, or NHATS, where we might have, thousands of people that we're building a model on, and maybe 50 potential characteristics of interest. These are just sort of orders of magnitude. And maybe the goal in that setting would be to build something like what you saw on the previous screens, where you have, a dozen or 24 predictors. That's clinically practical, but it's also sensible, but it also performs well. That's sort of proof of concept on the previous page that, such things exist and people find them interesting. We've probably moved more into this setting of late, where just like the previous, except we have a whole lot more, a much bigger N, maybe 1 million subjects, and a P, another 1 or 2 orders of magnitude larger, potentially, but still the same goal of trying to build something fairly parsimonious. It's not going to involve 500 predictors because we can't sort of use it in the cases we're thinking about. Models like this we tend to build in the EHR data from the VA, or from our university hospital systems, or from Medicare claims data. Okay. Obviously, everybody I'm sure on this call has been getting more into this newer setting of, what happens when you have really high dimensional irregular data on top of this: text data, image data, videos, intensively recorded vital signs. We're doing more about this in the last couple of years, but I'm not going to talk about this today. Okay, so of course, there's lots of different models that you might fit to kind of get at different types of predictions you're trying to make about people. I'm going to mostly focus today on logistic regression for simplicity, but we've done a lot of work with time to event models, multinomial outcomes. We've done some work with multi-state, and a lot of what I say applies to those, although every time you move down this ladder, things get a little more complex than they were in the logistic regression case. Okay, so so all of this is well known, right? Like, I shouldn't be giving a webinar about this because there's terrific resources on this, right? There's Harrell's paper or book on how you build a multivariable prognostic model. There's Steyerberg's papers and books. There's a guidelines, right? There's the tripod guidelines, and many papers about how to implement and details of the tripod guidelines. And so, you can kind of just go through these checklists and sort of feel that you're, doing a good job in building a multivariable prediction model and implementing it. In our group, we actually worked on and updating this tripod guidelines when you're working in older populations. So James Deardorff led a paper on this where we sort of gave some recommendations that were a little more tailor to doing prognostication in older populations. Okay. All right, so let's start a little bit with, I think this is the right place to start because it's sort of a big branching point. So there are probably people on this call who would never even think about doing regression modeling anymore. And there's sort of some reasons for that. And in many settings, machine learning, I think, is a much more powerful general toolkit to apply to the prediction problem. That said, there's a ton of stuff still in the traditional regression setting. And I think you'll find a lot of the work in the tripod author group is more focused on that. So, there's been some work of late. I think much of this was prompted by comments we were receiving. We would submit a grant proposal and say, oh, we're going to do some regression modeling. And someone would say, well, why aren't you doing machine learning? So we said, you know what, let's actually take a look at this. Where do you really get much benefit for fitting more complex machine learning models in the settings that we're interested in doing our prognostic modeling? So we have a paper about that. And then, we in this paper and in many others. I just give one example here. There's a paper by Austin, Harrell, and Steyerberg, sort of triple stamp of approval, I guess. They found that in their study that as we found, that traditional regression was extremely competitive with machine learning methods, and of course, much easier to attempt to explain in the types of calculator-based models that I was showing you earlier. Okay, so here's like a typical thing from our paper where across a huge range of types of models we might do, it's really, really hard to beat the C statistic of 0.83 this is a fairly large, it's like a couple 100,000 with 1,000 potential features from an EHR data set for predicting mortality. Okay, so if we're convinced that we can stick with traditional regression type approaches, what types of goals are we after in building these models, right? So of course we want a good model. It better be, very accurate. It should have, strong discrimination. It should be well calibrated. There should be sort of minimal overfitting that occurred in the process of making the model. It should be parsimonious for the reasons I've explained earlier, that you want to put these things, at least for now, on these apps and people, or web calculators, and people do want to be able to understand a limited number of inputs and how they are impacting, so interpretability, so how that limited number of inputs is impacting the prediction that it makes. And talk a little bit about this idea, which has caught our attention of late, which is the stability of individual predictions. I think I'll leave that for a second, and we'll come back to it. Okay, so what about overfitting? And this is a very well studied area, but why do you get overfitting when you fit a traditional regression model to a data set at hand, right? So right. What do? Well, we sit down, we make table one of all the variables. We do this before we make the model. We use table one to make the decisions. Do we sometimes look at bivariate associations? Probably. So there's sort of this kind of feature engineering, which is a little bit of an early peek at the data. Then there's some sort of variable selection. I'll talk a lot today about some lasso ideas, but there's other methods we've talked about before. And then there's some kind of hand tooling that happens after your lasso, where you say, well, I'd like to put something back in, or I'm not happy with the model it chose. I need to do something slightly different. And then, I think the part that if you've run any kind of these assessments of overfitting, parameter estimation is sort of often, pointed to as the thing that's most likely to lead to overfitting. The coefficients in whatever model you estimate are indeed optimized for the data at hand. Okay, but you can have overfitting from all three of these types of activities. So, how do people handle overfitting and assess it? You still see a lot of this single split sample where they take a data set, they divide it into development, and then they keep a part of it out for validation. This could not be more uniformly described as an inferior idea. There's a number of papers. I point out this one, this Collins et al. 2024. it led a series, it was a sort of the tripod author group, led a series of articles in the BMJ saying, it's like the first point in the paper is please don't split your data in half. Because with a single split sample, it's hard to separate the random variability from systematic overfitting, right? So it's much, much better to use some sort of bootstrap or cross-validated internal validation. Okay. I'm gonna have to here. So let's keep that in mind. Let's talk about some of the things that go into assessing the overfitting. Right. So what are we doing when I mention feature engineering? There's this whole idea of, are you going to have continuous variables? Are you going to treat them continuously? Maybe you'll build some spline models. Are you going to categorize them? Even though Frank Harrell would say, don't do that, we still do that because, clinical interest is still there. How are you going to group levels of categorical variables? Maybe either that you've made or that were sort of provided in the data set as such. Are you going to look at any interactions in the model? Okay, I'm going to have to pause for 1 second here. All right, so selection with lasso. So in terms of our selection, I'm going to talk a little bit about some of the desirable features we found recently with lasso. It makes it easy to sort of have variables you always include. And I think this is something we've really focused on of late, is it provides constraints. And so this is really helpful. I'll show an example in a second to ensure that the variables you get aren't showing up as sort of negative points or protective odds ratios in whatever panel display you are using to show how the model is actually working. We know why, if we fit a large model with many predictors in it, we might get some negative coefficients, even if each individual potential predictor is ostensibly a risk factor, but it sort of points away from kind of the believability of the model. And so in general, we often have a large set of risk factors, and we would like to put some of them into the model, and we would like them to have interpretations as risk factors once they enter the model. And so Lasso, has constrained versions of it that are really nice for doing this. There's other variants of Lasso that are useful for, categorical predictors, different shrinkage. You can use elastic net for sort of an less abrupt behavior. I'm not going to talk about that today. Here's an example visually of sort of what happens with Lasso. If you say, all right, I have some prediction model, go ahead and do some selection and estimation from a set of potential features, and it'll come back and say, all right, I've dropped a bunch of these that are the blank ones, and most of them indeed do show up as risk factors, but there's some here that are having these difficult to interpret odds ratios of less than 1. And so you'll sit down with an investigator and they'll say, I don't understand, how could sleep apnea be protective in predicting my outcome? And so certainly there might be a story there and might be useful to have such a model, but in general, we find that it's better often to say, tell Lasso, just select models that have risk factors, odds ratios bigger than 1. And, in this and in many cases, as I'll discuss soon, the models are going to have exactly the same predictive power, the same calibration, and this one will be sort of easier to interpret once we've constrained the potential predictors to have odds ratios over 1. Okay, so we talked about this idea of the feature engineering and the predictor selection of some sort, and then the actual estimation of whatever coefficients are going to be part of your traditional regression model. What do I mean then by bootstrapping for internal validation? And I'm sure many of you are very aware of this, but maybe a couple of you have not seen this before. So how do you do this? So it's pretty simple. You just sort of first you develop the prediction model in your full original data set and see what's its apparent performance, say a C statistic. Then you generate a bootstrap sample, same size as your original data, and redevelop your model in that bootstrap sample. And then you contrast what is the apparent performance of that bootstrapped, the model built on that bootstrap data, with the performance back in the original data, right? And just the fact that, whoops, we know that, in a bootstrap data set, you'll have about 37% of the observations are excluded from any particular bootstrap data set. So having just that little bit of kind of untapped data in every iteration of 3 allows you to get some sense. And there's fancier algorithms, like people talk about 632 and 632 plus that emphasize the left out observations more or less. But this basic idea of building the model in a bootstrap data set, checking how well it performed in that bootstrap data set, and contrasting that to how well it performs back in the original data, and then doing that a lot of times, is enough to establish how much overfitting is happening in step 1 here, when you just develop the model in the full data. And then you can correct for that as well. Okay, so now that said, if we go back to this step 3 here, it says develop a bootstrap model applying all the same modeling and predictor selection methods, right? And that's the tricky detail, because we need, as I was saying, we need to not just do the variable selection and the coefficient estimation. That's pretty easy to bootstrap. The feature engineering, though, is a big part of why overfitting might occur. And so thinking about how to do that, it's a little harder to algorithmize, right? So as I was saying, it's pretty straightforward to do selection and estimation. With and algorithmize that, obviously, but how might you algorithmize something like feature engineering? Well, you could imagine building in some ad hoc rules. You might have some sort of unsupervised thresholding algorithm. There was a nice talk about that on the statistics and data science webinar a few weeks ago. You might use some sort of supervised not finding if you really want to reflect the reality that probably there's some bivariate analyses happening before you build your model. Okay, so I want to think a little bit now about how much does this matter, I guess. When you have large data sets, do you really get very much overfitting? How much do you have to worry about it? And if you don't have to worry about it, what does that tell you? So this paper to me was a revelation, right? So I love the title, first of all, In Defense of the Indefensible, a Naive Approach to High Dimensional Inference. So they basically said, here's something that people do, which is not allowable by people who invented lasso, right? They fit lasso to select variables, and then they refit a regression model using that selected set. And then they make confidence intervals and p-values for the odds ratios from that second refit regression, right? So it's sort of using the data twice. It's kind of cheating. And the conclusion in this paper was that actually that's okay for many large data settings. Everything works out just fine. Don't worry as much as you think you need to worry. And so that kind of thinking carries over to some of these other things, like how much overfitting happens when you have a large sample size. In those, the variable selection and estimation, maybe in feature engineering. And the answer is not much, right? So if you have some of the data settings I was talking about earlier in the slides, 100,000 observations, 50,000 observations, and you don't have millions of potential predictors, not much overfitting can happen in a traditional regression setting, right? And so that's actually useful. So the apparent performance of fitting your regression model is probably not too different from sort of this optimism corrected, internally validated bootstrap performance. Okay. So an idea related to that I've been kind of thinking about of late is this leaderboard idea, right? So there's so much of statistical research is kind of focused on, the right model or the single best model, right? So, a lot of kind of statistical theory takes the oracle approach and says, if given the right model, what's the chance that as you have a large sample size, you'll identify the correct model? Um, that kind of goes against sort of wisdom from applied statistics, right? So we all know George Box's quote, essentially all models are wrong, but some are useful, right? And so my rewrite of that is something like, your model is not that special, right? And there's a number of ways to think about it. And in this setting, one helpful way is that there are a lot of models that will all have the same discrimination and calibration. I wrote acceptable discrimination. That's not even right, right? It's that you get the same discrimination to the third decimal place of the C statistic, and they're well calibrated, and they're different. They have different coefficients, different interpretations, different sets of variables, but they're all the same predictive power. So, it brings up this idea of thinking about the leaderboard, right? A large collection of good models, and some of them might be useful, right? So SAS had this idea when they introduced the best subset selection into some of their regression routines, into ProcReg and ProcLogistic. And I haven't really seen quite as good an implementation of this in other software, that you can sort of automatically get out this leaderboard. There's some other methods, of course, Bayesian or bootstrap selection can also get at the leaderboard idea, but I think, the idea of seeing that there's alternative models and knowing that they all have the same C statistic is a powerful idea, especially for your clinical collaborators. They may not understand that idea well from their statistical training. So, this constrained lasso idea is an example of that, right? So I fit two different lasso models. They have exactly the same C statistic, but they have qualitatively sort of different interpretations. Here's some work we did. We wrote some macros in SAS and published them in a proceedings paper. It takes the kind of the raw output from best subsets regression and takes the top some number of data sets and ranks them by other criteria which you might be interested in prognostic modeling, like the C statistic or the BIC or the AIC. And, obviously this is too small to see, but the idea is there's different models have different sets of predictors. And for any particular set of them, a clinical researcher might be tempted to craft a story related to that particular model. And so it's helpful for them to see, you know what, there were 20 models that all had a C statistic of 0.85. And they're slightly different. Kaggle, of course, is a great source for understanding this, right? So here's the leaderboard from some competition I just got off the net yesterday. They were trying to do some sort of binary prediction and they have to give their C statistics. And, every one of the top 500 entries had a C statistic of between 0.901 and 906, right? So there's really not very much to tell these entries apart. If entry one puts their model into industrial practice, they'll probably make a little bit more money. But, in terms of kind of clinical interpretation settings, it's not really going to matter if you use any of these models. And so we might as well use the one that's sort of most useful to us in some sense. Okay. All right. So let me pause here and kind of take stock of where we are. So, the general idea of, can we, use lasso methods to accomplish some of the goals that I laid out, right? So I know lasso is going to be very excellent for predictive accuracy. It's going to be good for minimal overfitting. It's going to be good for interpretability because it's a regression method. So it'll have, produce odds ratios. If I want sort of more interpretability, I can require it to select only positive coefficients, odds ratios bigger than 1 for some of my terms. And I can force in some other terms. So sort of that combination of things tends to make it easy to develop an interpretable model. Okay. So what about the other two, though? Is lasso parsimonious, right? I mean, if you took a poll of people on this call and you said, well, is lasso a parsimonious regression technique? I think everyone would say yes, because that's sort of how it was, pitched when it came out. Lasso is a way to select a parsimonious subset from a large list of predictors. I'll talk in a second. It's maybe not as parsimonious as you think. And then what about the stability of prediction? We'll come back to this because I need to talk about what that means first. Okay. So parsimony. There's been some work on looking at, how does lasso compare to more of these sort of L0 type methods like stepwise selection or best subsets. And maybe not that well known is that when you have a very large sample size relative to the number of potential predictors, Lasso picks a less parsimonious model than these sort of stepwise or best subset type methods. That was noted in a paper by Hasty and two Tibshiranis. We have a paper showing this kind of as you grow the sample size, the C statistics of, say, backward selection and lasso are going to be identical, but the lasso models are going to pick a couple hundred more variables than, say, backward selection. And, and that gap widens as the sample size gets larger and larger. And that can be an issue if you're really trying to kind of enforce parsimony on your model. It's really hard to get a very, very parsimonious lasso model because as you enforce more parsimony, the C statistic does start to degrade. Okay. So, as I was saying, I mean, we compared to things like stepwise and best subset. I think, some of those methods have kind of lost favor in the literature for sure. There's a newer implementation of a best subsets approximation method called broken adaptive ridge. It works really well on very large data sets, and there's a nice R package to do this. And they sort of found the same thing when they ran bar on these large data settings, lasso models, whether, we're picking 100 or 200 predictors. The, broken adaptive ridge models were picking 50 to 100 predictors. So it's, definitely more parsimonious and, kind of all achieving a similar C statistic. Okay. So now I'm going to kind of talk about my, this last idea. And I see in the, the chat, there's some other issues here. It's certainly not an exhaustive list of things that need to be good about a prediction model, but some of the ones I was talking about today are, we're getting towards the end of those. All right, so let's think about this leaderboard idea for a second. So we know from the leaderboard model that you can get a big list of models. They're all going to have the same C statistic. They're all going to be well calibrated. They're all going to be parsimonious if you take some sort of traditional regression approach. This is a problem, though, and it's not maybe that well described in the literature, which is that if you make your predictions with one model and you make your predictions with another model, an individual's predicted probabilities might be very different. And it's like much, way more different than, say, the confidence limit on those individual predictions would show. And this is undesirable, right? So you don't want people going from, they already have a lot of choice in their calculators online, and the list only grows by the day. And so the idea that people might get a very different prediction for their specific individual probabilities is a little bit of a problem, right? Because people will make decisions based on the probability. If you tell someone the probability is 43%, they might make a very different decision than if the probability is 23%. And so the idea that models that fit really well individually and really have nothing to recommend one versus the other, but that could give very different predictions from each other, is an issue. There's been some discussion of this I found in the machine learning literature, where they call the idea predictive multiplicity. I learned this from Berke Stun, and he has a paper with some of his colleagues that describes this nicely. This idea is not new to statistics either. I think the first pass at this was with reclassification metrics. There it was pitched more of, here's a way to decide if a new variable that you're trying to add into a regression model gives some value on top of the predictors that you already have. If that's true, then what you should find is that more people get correctly classified, into high risk from low risk, as opposed to low risk to high risk. So you should have this like net improvement of your reclassification when you add a new variable to the model. when you're comparing models that are similar, I don't know that the reclassification metrics have been used quite as much. That maybe fell out a little bit out of favor, as it certainly requires choosing of a threshold. There's versions of them that look across all possible thresholds for kind of making binarized predictions from probabilistic forecasts. There's another variant of this same issue that's been in a number of papers. Riley, one of the tripod author groups folks, has some models looking, I think his paper has some provocative title about the multiverse of predictions. And it's a similar issue. It's slightly different. He's thinking more about, how unstable are individual predictions across replicate data. So sort of bootstrapping the predictions that you might get from a model in parallel universes. But it is sort of a similar idea, especially if you factor in kind of the model building process to that. So this idea is, starting to show up a little bit. Here's sort of a toy example of this, instability of predictions, right? So there's been 7 NBA playoff games in the second round. 4 of them already have had someone with a 99% in-game probability of winning at some point that went on to lose the game, right? So, conceptually, if this is the same idea, right? I don't necessarily, certainly if this was a once in a century occurrence that somebody could go from the 99% win probability to 0%, I believe that. But if it's sort of happening all the time, there's some notion that maybe ESPN analytics models have a little bit of instability problems. And yes, this is a different setting. They're conditioning on evolving data, right? This is a dynamic prediction model, which we're not talking about here. But I think this is kind of, if you've ever watched one of these while you're watching a game, this might give you the sense that there's a number of these games where they're calling it a 99% in-game probability, and then it seems to switch drastically at the end. Okay, so here's another example from our work. So you could imagine, we have one of these prognostic models like I was showing on the original calculator page. What happens if you take, say, a 17 predictor model, you drop a variable and you refit it? Well, turns out the C statistic is about the same for most of these predictors, but you get wild instability of the predictions, right? So I'm trying to show this 2 ways. So in this way, I've sorted the predicted probabilities for each individual and then and plot those in black. And then I show in red what's the range of things that can happen to an individual person's probability as you drop one of the variables from the model. And you can see there's some pretty big swings. And then this this sort of Andy Warhol derivative looks at the same thing at the individual predictor level. So, how much here's the probability for the original probabilities of the outcome for each person are on the x-axis, and then how much that changes when you drop one of the variables from the models on the y-axis. And so most people don't change that much, but some of the people change quite a bit. So you get these funny lip plots like this. Okay. Right. So what models are going to be most, subject to this problem of predictive multiplicity? Well, certainly parsimonious models are going to suffer from this, right? Because as you take a model a variable in or out, things happen like I was trying to show you in the lip plots, right? So so in this sense, too much parsimony may not be a good thing, right? So maybe this suggests that modestly parsimonious models like, say, the lasso or the constrained lasso, or maybe elastic net, which is even less parsimonious, might help us to avoid instability of individual predictions as we, imagine moving across the leaderboard of models. We might want to think about this. This is sort of, kind of thoughts and work in progress. But the idea of, is there some kind of reference model to use here? Like that's something that's kind of approximating the correct model that is not subject to predictive multiplicity. So something, even less parsimonious, but maybe a little bit penalized, might be a good reference model to check instability against. So this is where some of the kind of machine learning, more sophisticated machine learning models maybe, although they're not outperforming the traditional regression models in terms of discrimination in our setting, they may in fact be helping with this problem of predictive multiplicity. And so they may, at the very least, be something we want to reference simpler models against. Okay, so I'll summarize, and then I know there's a number of questions in the chat, so I'll have a few minutes to take those. Okay, so there are certainly many competing goals in building prognostic models. And our use case here is definitely involving, using the individual predicted probability. So people want to plug in the risk factors and see the probability for their particular situation. And the number that they get means something. Right. So, I talked about this idea of you always have this top heavy leaderboard, right? So this is not golf from the Tiger Woods era. This is, this is the Kaggle problem. Everybody's model fits the same. And because of that, there's a lot of choice there. There really is no such thing as the best model in the prognostic model setting that we're thinking about. Okay, so the constrained lasso models that we've been working with certainly seem to satisfy many of these goals. We're able to get excellent discrimination and calibration, reduce our overfitting. They're very interpretable. They may be a little bit less parsimonious than we'd like. And they may or may not sort of suffer from predictive multiplicity to some degree. That's what I was just sort of saying. So in larger sample sizes, if parsimony is the goal, you may need to move more towards an L0 method, but then you may sort of run into more issues with predictive multiplicity. Okay, so thank everyone for coming and listening, and to Michelle for inviting me. And I have to say, I'm just delighted that this SDSA is off the ground, and I see, there were 100 and something people on the webinar, and it's just a remarkable thing you've built, and really glad to be part of the group and to get the opportunity to present today.
So thank you so much, John, for such a wonderful presentation. And, these kinds of groups, it's a team effort. And also, part of the team are the members and the folks who actively join our activities. So thank you all for coming. And we've had a very active Q&A. So we'll try to take as many questions as we can. So the first one is from Daniel Schulman. He's asking, under the list of goals of a predictive model, I noticed you didn't explicitly include any measure of fairness. And he's asking, do you have any practices and recommendations here?
Yes. So, we've been working on fairness metrics quite a bit. I'll just say a couple things in terms of how they play into here. I mean, I think certainly, interpretability of a model is kind of part of, certainly going to be part of the fairness investigation. I think, the idea that you have, where does predictive multiplicity sort of fit into this? Well, it definitely does. And one measure of fairness that I've seen discussed in that the Ustan and others literature is that, if you have more instability in certain groups of the predictions than in others, that is a measure of unfairness of the model. So if you're able to make predictions that are more, the predictions are more wiggly in some groups than others, then it may be less informative for some than others. And so it is definitely a goal to try to build models where the predictive stability is similar across groups as well.
Great. Charlie Beekman is asking, could it be problematic to constrain predictors to have odds ratios greater than 1 if you have not examined them in possible interactions?
Yeah, I mean, it's a terrific question. I mean, I think, this kind of gets to the root of, the goal of predictive modeling is not etiology, right? We're not trying to make a DAG and kind of, perform, make causal statements when we're done. So on the one hand, we don't really care. And I think that's where kind of the machine learning methods have been allowed to take off, is that, well, if you don't care, you can just put everything in and out pops a probability prediction and you know it's a good one. Or it could be a good one and you can check. That said, I think the flip side to that is, there really is still this strong interest in kind of these parsimonious prediction models. And when you have those, you're presenting your odds ratios in a table, and the idea that some of these factors are having a protective odds ratio, it really bugs the investigators or the consumers. And if you can avoid that, and the model, the story of the model makes some sense, I think that's a reasonable approach. We've also talked about, right, I mean, when you have a lot of candidate predictors, and if many of them are, continuous variables, to really pick up the predictive signal you'd need to be competitive with machine learning methods, you probably need to look at, at the very least, like spline encodings and some first order, some pairwise interactions of things. In practice, when we've looked for, I mean, most of our work has been in kind of binary indicators, presence or absence of a code in the claims or in the EHR. In that setting, the interactions don't matter that much in practice, right? I think Frank Harrell has some excellent posts on this I've seen before, that, from the predictive modeling standpoint, the interaction terms just don't add very much. The main effects can really pick up most of it. And, and to the extent that that's not true, yes, you can build in some model building across, say, a set of important interactions that you might consider that, would make sense in one of these calculator presentations.
Thank you. Orna Intrator is asking, how much overfitting can you get with large data sets?
Lorna, thanks for the question. Yes, so I think, I tried to get at that a little bit, and the answer is, I think not much in this setting, right? So when you have n is much bigger than p, and you're doing traditional regression type things, the amount of overfitting is actually pretty small. And that said, we still, if we're going to not have a separate holdout data set for validation, we do like to go through the ritual of doing the full internal validation. Although usually what it would show in a very large data set is that the C statistic might be overstated by 0.001 or less. But it's important to be able to quantify that. But I think that, so that's sort of one thread, is it, yes, with large data and n much bigger than p, traditional regression doesn't really seem to give you that much overfitting. The apparent performance is the performance. The the counterpoint to that is that, oh, I'm sorry, I lost the thread there. I'll stop with that.
All right,
Question?
Bill Wonderland is asking, how do you deal with recent changes, such as the rise in weight loss drugs? So I guess like a data shift issue.
That's a huge issue. Right. So I think you could imagine that any calculator that's been sort of developed doesn't have any knowledge of those types of things. And so, yeah, you'd have to think about, if you're really trying to uh, predict people's health, and there's some huge sea change, like, people are able to, reduce their weight, or they're on medication and, they've had health improvements, then yeah, that should certainly be something we start looking at routinely. Some in our group have started to work on some of these GLP projects, and I think there's a lot of interest there. But yeah, quite frankly, I mean, you saw we were looking at HRS data linked to Medicare. That data set is frozen in time at 2020 still, and so for our implementations of things, we haven't really come into that area yet.
Great. Daniel Schulman is asking, how does the leaderboard concept work with model interpretability? Do you present multiple interpretations, which may be overwhelming, or just the top model, or perhaps a single model average set of coefficients?
Yeah, no, that's a good question. I mean, I guess you could think about all three of them. Um, I'd say one way it helps to me is it gives humility to the investigator. If they can look at a leaderboard of models and see that, the one we're using is just one of many, and the other ones are a little bit different in terms of what variables are in there and what effects are showing up, that can help them to understand that, try not to write the paper so much about the model you chose. So that's one idea. A second idea would be, and I think this would go to say the issue of uh, predictive stability, predictive multiplicity, that, methods that use model averaging are going to be terrific at combating predictive multiplicity, but they're going to be, they're harder to understand, right? I mean, that's definitely going to be a trade-off there. You can't, if you basically tell people that we made 10 different models and each one made a prediction and then we average those to get your prediction, that can be a little harder to understand. However, that might in fact be the right thing to do.
Great. There's a couple of requests for you to share your slides. I'll email you offline so we can talk about that more. Josh Betts is asking, and I'll go through two more questions because I want to be mindful of the time. But when we see a negative coefficient that is a priori expected to be positive, a statistician would likely think about the uncertainty around the estimate. Lasso provides an estimate, but doesn't provide standard error. What about Bayesian regression with a horseshoe prior that does both selection and inference? Have you used this in practice as a point of comparison for Lasso, particularly when there's difficult to interpret sign issues?
Yeah, so I mean, there's obviously a number of parts to that question. I mean, I think in the settings we're in, if Lasso doesn't set something to zero, the confidence limit, and we talked about, if you purely follow the Lasso uh, idea, then you don't get confidence intervals or p-values. But there's certainly this other paper, and there's definitely practice where people use Lasso for selection and then they re-estimate the model in a typical, logistic regression package. The p-values for those things are all going to be highly significant in many of the settings that we're in. So it's not usually that you get something it's less than one, but it's crossing, the confidence limit would be crossing one a lot. In terms of like, yeah, is there certainly there's some Bayesian solutions here, I think that would be uh, helpful. I think, I've kind of gone back and forth in kind of how Bayesian my statistics have been across my career, and that's another trade-off of kind of complexity and interpretability. If you have a model that someone can fit with the software they have, they tend to, sort of have more faith in it, and it's less on kind of like, oh, I got this from my statistician. On the other hand, those Bayesian models are incredibly useful and very powerful. So I think that there's probably some trade-off there.
All right, I'm noticing the time, but I said I would do one more question. Um, no, I won't be offended if folks have to rush to their next meeting, but for those who want to stay for the last question, you're welcome to. And there's a question about what about external validation from an anonymous attendee? And this person says that they've seen that some studies require to test using external validation data, but some are not due to each model is data specific, or due to
Yeah,
each
so
model
this is
being
an
data
excellent
specific.
question. I think this comes up that, if you attempt to submit a paper where you say, we used all the data for training and we report internally validated performance, someone will say, well, you should externally validate it. And so there's some, I think there's still some value, although there's a, big debate about this. That BMJ series of prognostic model articles kind of makes the argument that if you have the external data available at the same time you're doing your original modeling, you ought to be including that external data set in the data set that you're using to train the model. But there are settings where the external data come later, and it's definitely worthwhile to take a previous model and externally validate it. or where like somehow the setting is so different that you can't think about combining across the data sources. And so I think there's still some excellent applications of external validation. And in fact, they do talk about in those those BMJ papers if you sort of want to see kind of the clinical view on that.
Okay, great. Thank you so much, John. This has been a very informative and practical presentation. And you're getting a lot of kudos in the chat, which is great to see. So thank you so much. And
Great. Thank you.
yes, and we're going to take a little break from the SDSA webinars over the summer, and then we will pick back up again, usually when the academic year starts, so probably starting in September. So if any folks would like to present or you want to nominate someone, we're always looking for good ideas and folks who have some great research that should be shared. So thank you all, everyone. Have a great rest of your day.
Well,
Bye,
thanks.
everyone.